Hello, everyone. Thanks so much for joining us today. My name is Nir Minerbi, CEO at Classiq, and let's go. So what I'm going to discuss today is how to getting closer, much closer towards quantum advantage with the right development of quantum software, how to do that in a scalable, optimized way, and also to be able to include domain experts, which are non-quantum experts, in the process. But first, for those who don't know us yet, so Classiq was established 2 years ago. We raised so far $50 million based in Israel, in the US, soon expanding our team also to Europe and Japan. Currently, we have a team of over 40 quantum software engineers and quantum information experts, which develop a quantum algorithm design platform that is already being used in several industries and academia. Among our investors, financial investors from the US, from Israel, and strategic investors like HPE, NTT, Samsung, Sumitomo Corporation, and two of the titans of chip design, Mr. Lip Bhutan and Mr. Harvey Jones. As a leading software player, we are partnering, of course, with the leading hardware providers and also with leading enterprises who already have a significant quantum computing activity or want to be there. And let's now discuss what we do, but before, let's discuss quantum readiness. So obviously, we all want to be quantum ready, and we all know that quantum readiness is about hardware and about software. The hardware is being, developed by the tech giants, and we trust them. We see different modalities, but great progress with all of the modalities, right? We see more qubits, better quality, and we have very good reasons to be optimistic that in the near future, we'll be able to run more coherent circuits on hundreds and thousands and more qubits. And then it would be a fair question to ask, are we ready for these circuits? And the honest answer is probably not, because with existing tools and methods, as we all know, it's fairly reasonable to design small toy circuits for 5, 7, 10 qubits. It's very, very challenging to design more complex circuits for a few dozen qubits, and it's practically impossible to design reasonable circuits for hundreds, thousands, and more qubits, because this is just too complex design challenge with existing tools and platforms. And I want to give one simple example. So most of us know the Grover oracle, and actually generating such oracle is a nice exercise to be done on 3, 4 qubits. And actually this circuit will mark 2 out of 8 states. And the oracle is very simple, right? Is on 3 qubits, and this could be hand coded. But what if we want to design a more complex oracle? Let's say we want to define 3 quantum registers, A, B, and C, that apply to this arithmetic arithmetic expression, A plus B plus C and 15, so on and so forth, equals 4. Now, take 1 or 2 seconds to think, how would you implement this circuit? It's challenging, right? And indeed, you see that this oracle, this circuit, is quite complex. Each of these boxes are functions, and when you open these functions, you have internal functions, and eventually you get quite a complex quantum circuit. And this is a small circuit, right? This is only on 22 qubits. Now, think of designing such circuit for 1,000 qubits. So this is one challenge. But now let's dive into some of the circuit design challenges and then move to the Classiq solution. So when we design a quantum circuit, we have on the one hand block level decisions, because for one block, there are many possible implementations. You can use different number of auxiliary qubits. you can achieve different levels of accuracy. But on the other hand, you then need to take care of the system-wide constraints, like the overall number of qubits, the overall circuit depth and CNOT gates, and of course the hardware, the preferred gate sets and noise model and connectivity. And the main problem is that you can't really divide these issues, right? They are deeply interconnected. Another challenge is that when you design a quantum circuit, you need to manually, explore a huge design space. And I want to give an example to what I mean. So you see here 3 different quantum circuits, very different, right? But you can believe me that their functionality is the same, right? They achieve the very same functionality. Now, flexibility could be, you could think of it as a good thing, but it's not a good thing because, you can achieve in a naive way a large, not a non-optimized quantum circuit, but possibly in the design space, you could achieve the very same functionality with 10% of the resources. So this design space is also a great challenge. And the funny thing is that eventually, after we explore the design space and find the right quantum circuit for us, we leave the last mile for automation, right? We wouldn't think of compiling or transpiling manually. But then we leave the compiler with a very low flexibility, right? Because it gets as input a gate level circuit, and it's bounded to get to keep the very same gate level functionality. So, okay, so this is another challenge. Again, now if I need to summarize some of the major challenges in quantum circuit design today, is first building quantum circuits that scale, right? As we showed before, it's relatively easy to design small circuits. It's very challenging to scale. Then you need to navigate a huge design space and choose the best design choice for the resources and constraints you have. You need to trade off manually the functionality versus constraints. And then eventually, if you are not a quantum expert and you want to embed domain experts in the process, it's also very challenging with existing level of abstractions. So these are the challenges that we are solving in Classiq. And if I need to summarize in one sentence what our platform does, so the Classiq platform synthesizes gate-level circuits from high-level functional models, and by that it enables the design of state-of-the-art quantum circuits. This is our goal. Our goal is to enable you to design the state-of-the-art quantum circuits, to do that more easily and much more optimized and scalable. So obviously, as I said before, what we do is to solve this complex design challenge. And when doing that, we took our inspiration from another complex design challenge that was already solved, right? And this is chip design. So what you see here, this is an electronic circuit, not a very complex one, but yet it wouldn't make a lot of sense to design it at the gate level. And luckily, we don't need to do that, right? Because in the classical world, we have high-level modeling languages like VHDL, like Verilog, and synthesis tools like Cadence and Synopsys, which allow us to define a high-level functional model, but leave a gate-level implementation to automation. And this is essentially what we bring to the quantum world. The ability to define a high-level functional model of the quantum circuit. In this case, so you define the Grover oracle, like I showed before. You define the arithmetic expression of the oracle, the constraints like qubit count. You define the output format to be Q-sharp, and then that's all, right? The rest is done by the synthesis engine, which takes the high-level model and gives you a gate-level implementation, which is also optimized. Now let's take a look at the flow. So basically, the quantum algorithm developer in Classiq defines the functional model and also the constraints. On the one hand, if you don't know on which hardware you're going to run it, that's okay, right? The circuit could be agnostic. On the other hand, if you do know that you're going to run it on superconducting qubits or ion traps or any specific architecture, you can embed as configuration file the constraints, the connectivity, the preferred gates, the noise model, the number of qubits, and so on and so forth. Then the synthesis engine gives you the optimal quantum circuit, and you choose the output language. It could be Qiskit, Q-sharp, QRR, circ, bracket, and so on and so forth. You compile it and you run on basically every quantum cloud you choose. As I said before, we have very deep relationship with Amazon, Microsoft, IBM, and many other hardware vendors like CodeQuanta. So basically, you can design the quantum circuit on our platform and very easily run it on the backend of your choice, also on simulators as NVIDIA's and others. So if I need to summarize before we jump into some examples, what the Classiq platform enables you to do. So first of all, it enables you to build sophisticated state-of-the-art quantum circuits in a scalable way. Then, of course, it also enables you to reduce by orders of magnitude, and I'm going to give one or two examples, the required resources, the qubits, the depths, the number of gates, and so on and so forth. It also makes the development much easier. It dramatically reduces the development time. It enables you to embed domain experts, which are non-quantum experts, into the quantum computing software workflow. And maybe most important, and if not one of the most important, so it enables you to create and keep your own IP, right? You don't need anyone to design your own algorithms and circuits. It is easy for you to design custom functions and your custom models and to keep the IP. Now I want to give two examples of the superiority of this layer of the stack over gate level design. So the first one will be in chemistry. So in chemistry, as we all know, we can't yet simulate large molecules, but what we can do is first getting ready for that, right? Being able to design ansatz and the entire VQE scheme for large molecules, and to check our results on small molecules. And the gold standard today is H2O, water. And what you see here is when applying the Jordan-Wigner mapping and the UCC ansatz in the Classiq platform, and comparing it to the state of the art after transpilation, you save more than 50% in resources. And that's incredible because this is mathematically proof that the final results with both platforms are identical. And this is the power of optimizing in the model level, because there are, you can explore the design space and get much better optimization than you could get only with transpilation or compilation. And this is for small molecule. When you get to larger molecules, the saving achieved with Classiq are even more dramatic. So this is one example. Another example is optimization solver. In this case, the 3-sat optimization solver is good for several use cases. One of them is formal verification. And what I want to show here is the entire flow, right? So first, you need to define what functionality you want to achieve. So in this case, this is the functionality, right? 3 quantum registers that should apply to these clauses, right? And then you also need to define the constraints. So in this case, the constraints are on the overall qubit count and the maximal circuit depth. And eventually you need to choose the backend of your choice, in this case, a simulator, and then you get, you first generate quantum circuit, and you can get very different circuits, each optimized for specific optimization criteria. So the first one, which of course was automatically generated, is optimized for circuit depths, right? This is the most shallower circuit, and you see that it uses 13 qubits. On the other hand, you could choose optimization for the qubit count. So this one uses only 8 qubits, but it's more deep. And if you know on which hardware you're going to run, you can optimize for the overall accuracy using 12 qubits in in specific circuit depth, but it is guaranteed to you that this is the best solution for the chosen machine. And now I want to give to take it to the next step, because this was a relatively simple example of 3-SAT. But what if you want to apply much more complex functionality? In this case, a K-SAT optimization solver, 4-SAT actually, and it's much more complex, right? This is the functionality you want to achieve. So then how would you implement it? It's very challenging. And let's take a look at the circuit that was automatically synthesized with the Classiq platform. And you see that this is already quite complex. You see here many functions. You can open the function and you get internal functions. And actually, this is quite a complex, sorry. But I think that the incredible thing here is that this circuit was synthesized automatically. It took like 5 or 6 seconds, and it's very complex, right? Complex, optimized, and this is the way to go when you want to design complex, sophisticated, state-of-the-art quantum circuits. Great. So eventually, I want to describe how customers use Classiq today. So customers, on the one hand, can easily use the application suites of pre-built models in finance, in chemistry, in QML, optimization, cybersecurity. But on top of that, they can easily create and use custom functions, right? They can create their own IP, and they do that, and then, of course, run it on the backend of their choice. So here you see some of the applications developed by our users. So this one is the value at risk circuit. In finance, this one is a QAOA-based portfolio optimization, also in finance. And of course, there are many other examples which all connect us to the same place. And this is being ready with quantum software, being ready to scale with the state-of-the-art quantum circuits that will bring the first and second and third and many more occasions of quantum advantage. Thank you so much, and I would really love to answer any questions now or over email. Thank you. Bye-bye.